Good morning, students. Very good morning. Today we have lecture number 2 on alternating current. Lecture number 2 on alternating current. In the first period, in the previous class, we have started alternating current. Lecture number 1 on alternating current, and we have understood what is alternating current and what is alternating EMF and what are the equations used to write that, and then we have understood that average value of alternating current, RMS value of alternating current, etc. Okay. So now, to measure the alternating current or to measure the alternating current, we cannot use the ordinary moving coil galvanometer. We cannot use the ordinary moving coil galvanometer because that ordinary moving coil galvanometer is depending upon the magnetic effect of electric current. That is, it depends upon the direction. Whereas the direction of alternating current is continuously changes. So hence, to measure the alternating current or alternating voltages, we use AC emitters and AC voltmeters. AC emitters and AC voltmeters are used to measure the alternating current or alternating voltages or alternating potential differences. And these AC emitters and AC voltmeters are based on the principle of heating effect of electric current. They are based on the principle of heating effect of electric current. Hence, they are also called as hot wire instruments. These AC emitters and AC voltmeters are called hot wire instruments. Understood? Okay. And then this AC emitter, the AC that is alternating current and alternating voltages can be represented graphically, by using phasors. So what is a phasor? So next concept we study about phasor. A phasor is a rotating vector. A phasor is a rotating vector used to represent a quantity. A phasor is a rotating vector. What type of vector? Rotating vector used to represent a quantity. It is used to represent a quantity, and that quantity must be sinusoidally varying with time. A sinusoidally varying quantity, time varying quantity can be represented in the form of a rotating vector, and that rotating vector is called as phasor. A phasor is a rotating vector which is used to represent a quantity which varies sinusoidally with time, which varies harmonically. That is, harmonically varying quantities can be used to represent them as vectors. So that is, actually this alternating current and alternating voltages are not vectors, they are scalars only, but they are represented as if they are vectors because they are harmonically varying quantities. A harmonically varying quantities can be represented. So by using harmonically varying scalars can be represented as rotating vectors. So having the corresponding magnitude and direction. Okay. So what is a phasor? A phasor is a rotating vector which is used to represent a quantity which varies sinusoidally with time. A harmonically varying quantity can be represented as a rotating vector, and that rotating vector we call it as a phasor. Okay. So it is, so a graph is drawn and this is called as phasor. The length of the phasor gives for example, the alternating EMF. The alternating EMF is given by V is equal to V naught sin omega t. V is equal to V naught sin omega t, or you can write E is equal to E naught sin omega t. Same formula only, I am writing like this. V is equal to V naught sin omega t. So here the length of this phasor, gives V naught, that is the maximum value. The maximum value of the quantity is represented by the length of the phasor, and omega t, that is angle. The phasor, this vector makes an angle omega t with time axis or with x axis. So this angle is represented like this, and the value v, that is v, instantaneous value of this vector, the instantaneous value of the vector is represented by the projection. This projection will give the value of v. This projection of the phasor on a fixed axis, the projection of the phasor on a fixed axis will give the instantaneous value. The projection of the phasor, this is the phasor, the projection of the phasor on a fixed axis gives the instantaneous value, and the length of the phasor, the length of the phasor gives the amplitude of the quantity, the length of the phasor gives the amplitude of the quantity, and the angle made by the phasor with the axis, x axis, will give you the that particular angle, that is omega t or theta. Understood? So that is actually this is not a vector, this is a scalar, but it is harmonically varying a scalar. What type of scalar? Harmonically varying scalar. A harmonically varying scalar can be represented as a projection of a rotating vector, can be represented as a projection of a rotating vector. It is a rotating vector, and this rotating vector is called phasor, and the angular velocity of this rotating vector, the angular velocity of this rotating vector is same as the angular frequency of the quantity. Angular velocity of the rotating vector is same as the angular frequency of the quantity. Understood? And the vector, this phasor vector is considered to be rotates in anti-clockwise direction. It rotates in anti-clockwise direction. Understood? Okay, these all are the information regarding phasor. So a phasor is a rotating vector which is used to represent, the quantity which varies sinusoidally with time. A quantity which varies sinusoidally with time can be represented as rotating vector, and that rotating vector is called as phasor. Understood? And the length of the phasor will give the amplitude, and the projection of the phasor on the fixed axis, on any of the fixed axis, gives the instantaneous value of that quantity, and the angular velocity of the phasor, the angular speed or angular velocity of the phasor will be same as the angular frequency of the quantity. Understood? Okay. So this is about phasor. So by doing so, by making alternating current and alternating vector, by representing them as alternating current and alternating voltage are scalar quantities, and they are represented as phasor. By doing so, we can use the law of vector additions, to add these quantities. To add the alternating current or alternating voltages, we can use the law of vector addition when by applying them as a phasors, Understood? Okay. What is a phasor diagram? So they may ask in the exam, what is a phasor diagram? A diagram representing alternating current and voltages, as phasors, a diagram representing alternating current and voltages as rotating vectors or rotating phasors along with proper phase angles, is called phasor diagram. A diagram representing alternating current and alternating voltage as rotating vectors. A diagram representing alternating current and alternating voltage as rotating vectors along with proper phase angle, is called as phasor diagram. Understood? Okay. Did you understood all these things? Okay. So if this is a alternating voltage and this is a alternating current, then there will be a angle, phase angle between alternating voltage and alternating current, and this phase angle we call it as phase difference between voltage and current. Understood? Okay. Hope you understood this concept of phasor. Okay. So now the alternating voltage applied to a pure resistive circuit, alternating voltage, that is AC, alternating voltage. Alternating voltage applied to a resistive circuit. Okay. So now an AC source connected to a resistor. An AC source. We know the circuit diagram of AC source. Circuit symbol of AC source. This is AC source. An AC source connected to a resistor. Capital R as shown in the figure. And this is called pure resistive circuit. It is called as a pure resistive circuit. An AC source applied to a resistor. An AC source applied to a resistor, capital R as shown in the figure. And it is called as a pure resistive circuit. An AC source, that is the AC voltage applied, the instantaneous value of the AC voltage applied, instantaneous value of AC voltage applied is given by V is equal to V naught sin omega t. V is equal to V naught sin omega t. As a result of that, a current flows through the resistor. And according to Ohm's law, the potential difference across the resistor, is given by V is equal to I into R. Potential difference across the resistor is given by V is equal to I into R. Therefore, we can write I is equal to V divided by R. Therefore, I is equal to, use this equation number 1 here. So, V, instead of V, substitute this one, that is I is equal to V naught sin omega t divided by R. That is I is equal to V naught divided by R into sin omega t, or I is equal to I naught into sin omega t. So, where this equation number 2. Where I naught is equal to V naught divided by R is called maximum current or peak value of current. So this is the expression for alternating current obtained. When an alternating voltage is applied to a pure resistive circuit. Understood? So this is 5 marks derivation. This much only 5 marks it is. In the beginning it is not so much clear. When then we do next another 2 derivations, then it will be very much clear. Okay. So just try to understand. A AC source is connected to a resistor, capital R, as shown in the figure, and it is called pure resistive circuit. The instantaneous value of the AC voltage applied is given by V is equal to V naught sin omega t, where V naught is peak value of the voltage applied. And now, as a result of this applied AC voltage, an current flows through the circuit, an alternating current flows through the resistor. And according to Ohm's law, the potential difference, that is the instantaneous potential difference, you say instantaneous potential difference across the resistor is given by V is equal to I into R. So therefore I is equal to V by R. So I is equal to V. Substitute this value. It is V naught sin omega t divided by R, and V naught by R, that is nothing but I naught. So I is equal to I naught sin omega t, where I naught is equal to V naught by R is called peak value of AC current, and this formula gives the alternating current flowing through the resistor. So now comparing the equation 1 and 2, we understand that the alternating voltage and alternating current, both will have 0 or both will have maximum value or minimum value simultaneously. That is 0 value or maximum value or minimum value, both, that is alternating current, alternating voltage and alternating current, both will have at the same time. That is when omega t is equal to 0 degree, when omega t is equal to 0 degree, then alternating voltage, that is V is equal to omega t sine of 0 degree is 0, so V is equal to 0 and I is equal to also 0. Substitute this value in equation 1 and 2. That means alternating voltage has become 0 and alternating current also becomes 0 at the same instant of time, understood? And when omega t is equal to, when omega t, that is nothing but theta, is equal to, that is pi by 2, and then the alternating voltage V is equal to, so apply sine of pi by 2 is 1, so V is equal to V naught, and I is equal to sine of pi by 2 is 1, so I is equal to also I naught and V naught are maximum values, that is alternating voltage and alternating current are becoming maximum. Alternating voltage and alternating current are becoming maximum simultaneously when omega t is equal to pi by 2. So this shows that both are varying in phase, that is when voltage becomes maximum, then current also becomes maximum. When voltage becomes minimum, the current will also becomes minimum. So that is they are varying in phase. The alternating voltage and alternating current are in phase in a pure resistive circuit, when it passes through a pure resistive circuit. So if you draw a graph, that is graph for alternating current and alternating voltage. So that is I'll use two checks. So this is when omega t is equal to 0. So this is 0. This is, take it as pi by 2. Take it as pi. Take it as 3 pi by 2. This is okay. So this is 3 pi by 2 and this is 2 pi. Okay. This is capital T. So this is T by 2. And this is T by 4 and this is 0. Okay. So now first it will become maximum at pi by 2 and minimum at 0. So now once again it will becomes maximum and it will become 0. So this is for voltage. This is for AC voltage. So it is okay. Similarly, that is by applying omega t is equal to 0, omega t is equal to pi by 2, omega t is equal to pi, omega t is equal to, so if you apply all the things, we'll get like this graph. And similarly, for the current, if you apply the same values in the current, then also the values obtained will be simultaneously, that is simultaneously it becomes maximum and simultaneously it becomes minimum. So this represent alternating current. The dotted line represent alternating current. So AC current. So this represent AC voltage and this represent AC current. And AC current is also becoming maximum and minimum at the same instant. So this is called graphical representation. And now phasor. Now we have to try a phasor diagram. Phasor diagram for alternating current and alternating voltage. Here only I will draw the phasor diagram. It is so this is a phasor, that is a rotating vector representing alternating voltage. A rotating vector representing alternating voltage, AC voltage. So that is V is equal to V naught sin omega t. V is equal to V naught sin omega t, and projection of this on this, that is this will give the value of V. This will give the value of V, and this length will give the V naught. The length will give the V naught, and this angle made by that phasor with x-axis will give omega t. Understood? And now alternating current is also another phasor. Another rotating vector represented on the same, that is this is alternating current. So this is for AC current, that is I is equal to I naught sin omega t. And this also the maximum value, that is maximum value is given by length. The maximum value is given by length, that is this will give I naught and this will give V naught, right? And the projection of this phasor on fixed axis, this value, this will give the instantaneous value of current. That is instantaneous value of alternating current. And the angle is also same. The angle is also omega t. And thus, what is the angle between alternating current and alternating voltage when there is a resistive circuit? When there is a resistive circuit, that is, alternating current and alternating voltage are in phase. That is, the phase difference between between current and voltage, AC current and voltage is zero when they pass through a resistor. So it is when alternating current and alternating voltages passes through a resistor, the phase difference between alternating current and voltage is 0. That means they become simultaneously maximum and simultaneously minimum. Understood? So this carries pi marks. How much is this much? So it is pi marks derivation. Alternating voltage applied to a resistive circuit. Hope you understood. You understood the phasor diagram. Hope you understood the phasor diagram. And this phasor diagram you have to draw. And you have to write this explanation. That is, this explanation is very important. The phase difference between AC current and voltage is 0 when the AC current and voltage passes through the resistor. Understood? Okay. Now, in the next concept, that is alternating voltage applied to a inductor circuit. Alternating voltage applied to a inductor circuit instead of resistor. If there is a inductor, then what happens? We have to study. That is also for 5 marks, and these all are important derivations for the theory exam. These 3 derivations are there. That is, alternating voltage applied to a resistive circuit, one derivation. Alternating voltage applied to a inductive circuit, and alternating voltage applied to a capacitive circuit. So these 3 derivations are important. So these 3 derivations each carries 5 marks, and many times they are asked in the exam. Understood? So this is phasor diagram, and this is graphical representation of alternating voltage or current. Voltage or current along y-axis, and time or omega t, that is theta, is along this one. Understood? Next concept. Okay. So now let us study alternating voltage applied to an inductive circuit. Alternating voltage applied to an inductive circuit or AC circuit containing only inductor. Another heading for this one is AC circuit containing only an inductor. An AC circuit containing only an inductor. Okay. So now the same way, but there will be difference in the mathematics and difference in the graphs. And what happens? Whether there exists a phase difference between current and voltage or not. Let us find out. Whether current and voltage simultaneously become maximum and simultaneously become minimum, or they differ. So let us find out. Now let us consider a circuit containing a pure inductor of inductance L. Let us consider a circuit containing a pure inductor of inductance L connected to an AC source. As shown in figure. Connected to an AC source as shown in a figure. Let us consider an inductor of pure inductor of inductance L connected to an AC source as shown in figure. The instantaneous value of the applied EMF, is given by V is equal to V naught sin omega t. V is equal to V naught sin omega t. Call this as equation number 1. the instantaneous value of applied AC voltage is given by V is equal to V naught sin omega t. As this alternating current flows through the inductor, a induced EMF, a back EMF is induced. A back EMF is induced in the inductor, and the induced EMF, the EMF induced in the inductor, the induced EMF in the inductor, induced EMF in a inductor is given by E is equal to minus L di by dt, minus L di by dt. This is all the things we have studied in electromagnetic induction. The EMF induced in the inductor is given by E is equal to minus L di by dt. So now the net instantaneous EMF, the net instantaneous EMF is equal to, that is V minus E, that is V naught sin omega t, V naught sin omega t minus L di by dt, and this net instantaneous EMF must be equal to 0. This net instantaneous EMF must be 0, because there is no resistance in the circuit. The resistance in the circuit is 0. It is a pure inductive circuit. There is no resistivity. The resistivity of inductor is considered to be negligible. The resistance of the inductor is considered to be negligible. So there is no resistance. Therefore, the net instantaneous EMF must be 0, because there is no resistance in the circuit. There is no resistance in the circuit. So that is V naught sin omega t minus V naught sin omega t. Instead of V naught sin omega t, we just write it as V. You just write it as V minus L di by dt. So that is V minus L di by dt must be equal to 0. So therefore V is equal to L di by dt. V is equal to L di by dt. So therefore di is equal to, so thus we can write di is equal to V by L dt. V by L dt. Understood? V by L dt. So it is di is equal to V naught by L sin omega t dt, sin omega t dt. So now for this is small amount of current, for total current, for total AC current, integrating on both sides, so that is integration of di is equal to integration of V naught by L sin omega t dt, and V naught by L is a constant, taken it outside, V naught by L, and integration of sin omega t dt will come so to be minus cos omega t divided by omega, So hence you can write integration of di is nothing but I. So I is equal to minus V naught divided by omega L, into cos omega t, and cos omega t can be done as, that is cos theta is equal to sin pi by 2 minus theta, that is sin pi by 2 minus theta, that is omega t. So therefore that since cos omega t is equal to sin pi by 2 minus omega t, so therefore, shall I remove this diagram? So therefore we can write I is equal to minus V naught divided by omega L, this is not omega t, omega and L, minus V naught divided by omega L, cos omega t we can write it as sin pi by 2 minus omega t, and now further we can write I is equal to I is equal to V naught divided by omega L into sin omega t minus pi by 2. This is because minus sin theta is equal to sin of minus theta. Minus sin theta is equal to sin of minus theta. So therefore, you can write sin pi by 2 minus omega t as sin omega t minus pi by 2, removing this negative sign. Understood? So thus, so now let I naught is equal let V naught divided by omega L is equal to I naught. Then that is then I is equal to I naught sin omega t minus pi by 2, sin omega t minus pi by 2. So this is the value of instantaneous current obtained in an pure inductive circuit. Instantaneous current obtained in an pure inductive circuit. So now comparing equation 1 and 2. This equation 1 is the instantaneous value of applied EMF, and this is the instantaneous value of AC current, instantaneous value of AC voltage and instantaneous value of AC current when there is a pure inductive circuit. So now comparing equation 1 and 2, we observe that, we find that there is a phase difference, there is a phase angle of pi by 2, between AC voltage and AC current in a pure inductive circuit. In a pure inductive circuit, there is a phase angle, there is a phase difference of pi by 2 between AC voltage and AC current, and thus this is minus pi by 2. That means current lags behind the voltage. In a pure inductive circuit, the current lags behind the voltage by a phase angle of pi by 2. Just by comparing the equation 1 and 2, we can explain that the current lags behind the voltage by a phase angle of pi by 2 in a pure inductive circuit. So thus the phase difference exists between AC current and AC voltage in a pure inductive circuit, and the phase difference between current and voltage is pi by 2. And who leads? That is voltage, that is AC voltage. Voltage leads the current in a inductive circuit. When there is an inductor, the voltage leads the current. Understood? So that is, so now drawing the graph. So if you draw the graph, that is the variation. That is, both will not become simultaneously maximum and simultaneously minimum. Like in the previous derivation. In the previous derivation, that is when there is a resistor in the circuit, the instantaneous EMF and instantaneous current, both were becoming simultaneously maximum and simultaneously minimum. But here, they will not become simultaneously maximum and minimum. So there exists a phase difference. So now if you draw the graph, first draw the graph, it is voltage or current along y-axis, and along x-axis omega t or small t. Okay. So now first draw for AC voltage, that is applied voltage. So this is applied AC voltage. So this angle is 0. So here it is pi by 2, and here it is pi, and here it is 3 pi by 2, and here it is 2 pi. Okay. So now this is V naught. This is V naught and this is minus V naught. Okay. Okay. So this is AC voltage. And now AC current. Now AC current is having a minus pi by 2. Hence it will start from negative, that is minus pi by 2 from here. So minus pi by 2. So then we will draw the graph. So this graph is better if you see it in the books. So the graph is like this. So the graph obtained will be something like this. Okay. So this is better. Okay. So something like this. So you will get this is AC current. AC current, and see here, when AC voltage is maximum, AC current is not maximum, and here it is maximum. Okay, so like this you can get. So the graph is better seen from the book. This graph is better referred from the book. Okay. So thus there exists a phase difference. There exists a phase difference between alternating current and alternating voltage in a pure inductive circuit, and current lags behind the voltage. The current lags behind the voltage by a phase angle of pi by 2. The current, that is the current lags behind voltage by phase angle pi by 2, by phase angle pi by 2 in a pure inductive circuit, understood? Okay, so now phasor diagram. Now we have to draw the phasor diagram. So phasor diagram, that is this is a phasor, so fixed, this is fixed for AC voltage. AC voltage is remaining fixed, so that is V0. So this is for AC voltage. V is equal to V0 sin omega t. So from here to here omega t, and this is V0, and this represent, that is the projection represents value of V, and now from the equation I is equal to I0 sin omega t minus pi by 2, so omega t is here, so minus pi by 2, so minus pi by 2, so from here to here it must be pi by 2, minus, not plus, minus pi by 2, so that's why here, so this is I is equal to I0 sin omega t minus pi by 2, understood? So this is I0 maximum value comes here. The projection of this phase on a fixed axis will give the value of I. So instantaneous value of I is given here, understood? So this is called a phasor diagram. It is called as the phasor diagram. The phase difference between a current and voltage is pi by 2 as per the equation. By looking at the equation you can draw this phasor diagram, understood? Okay. So this represent AC voltage, that is V is equal to V0 sin omega t, and this is I is equal to I0 sin omega t minus pi by 2. So hence minus pi by 2, understood? So this is for 5 marks. It is alternating voltage applied to a inductive circuit. Understood the concept? It's very easy and very important. And drawing the phasor diagram also they will ask. So you have to write this derivation and along with that phasor diagram. This phasor diagram is important, and you have to draw that phasor diagram for 5 marks. Understood? Okay. So now from this derivation, so here some more things are there. So we have considered, that is V0 divided by omega L is equal to I0. It is the V0 divided by omega L is equal to I0. So comparing this with I0 is equal to V divided by R. Comparing this with I0 is equal to V divided by R. So we find that I0 is equal to V0 divided by R. We find that the omega L has the same role as resistance in a conductor. The factor omega L in inductor, the factor omega L in the inductor has the same role as resistance in the conductor. And let us say this omega as, let us take this omega L is equal to XL. We take this omega L as XL. So therefore V0 divided by XL is equal to I0. And XL is called inductive reactance. It is called as inductive reactance. XL is called inductive reactance. And inductive reactance, what is inductive reactance? The opposition offered by the inductor. The opposition offered by the inductor for the flow of AC current. For the flow of AC current is called as inductive reactance. The opposition offered by the inductor for the flow of AC current is called as inductive reactance. Understood? And the dimension and unit of inductive reactance are same as that of resistance. The dimension and units of inductive reactance are same as that of resistance, that is XL is measured in terms of ohm. XL is measured in terms of ohm. So XL is equal to, formula is omega into L. So XL is equal to L into omega is written as 2 pi f. L is written as 2 pi f. Understood? So XL is equal to 2 pi f. 2 pi f into L. Remember this formula. So to find XL, so the formula is 2 pi f into L, where f is the frequency. Where f is the frequency. Understood? And now let us see how this inductor will behave with DC current and AC current. How this inductor will behave with DC current and AC current. So for DC current, the frequency of DC current will be 0. The frequency will be 0. So therefore inductive reactance is 0. That means the inductor does not oppose us the DC current. The inductor does not oppose us the DC current. That is, the DC current can flow very easily. The DC current can flow easily through a inductor. The inductor does not oppose the flow of DC current. And now for AC current. For AC current, so there will be a value of F. The frequency of AC will not be 0. The frequency of AC will not be 0. There will be some certain value of frequency. For example, in our household circuits, in our household AC voltage applied, the applied frequency is generally 50 Hz. In India, in our household circuits, the frequency is 50 Hz. So, and in some time it may be 60 Hz, 40 Hz, depends. But generally it will be 50 Hz in India. So it will have a finite value. So not 50 Hz. So it will have a finite value, a fixed value. A finite value will be there. So therefore XL will be a finite value. XL will be a finite value. That means there is a opposition to the flow of AC current. An inductor will oppose us the flow of AC current. So XL is equal to, you will get some value. That means there is a inductive reactance for the AC current. That means inductor opposes the flow of AC current, whereas inductor does not oppose us the flow of DC current. A inductor opposes the flow of AC current and does not oppose us the flow of DC current. And the opposition, that is inductive reactance, is directly proportional to the frequency of the AC. The inductive reactance is directly proportional to the frequency of the AC. So if we draw a graph of variation of XL with frequency, the graph obtained will be a straight line. The graph obtained will be a straight line with positive slope. The graph obtained will be a straight line with a positive slope. That is, as frequency of AC increases, the opposition offered by the inductor for the flow of AC will also increases. As the frequency of AC increases, the opposition offered by the inductor for the flow of AC will also increases. So F increases, XL will also increases. Understood? This is the concept of alternating voltage applied to a inductive circuit. Understood? Okay. So in the next class, so today's time is up. So in the next class, we will study alternating voltage applied to a capacitive circuit. If there is a capacitor, what happens? Today we have studied what happens if there is a resistor and what happens if there is a inductor. And now in the next class we study if there is a capacitor, then what happens to the AC current. Whether AC current, there exists a phase difference between AC current and AC voltage or not. So that when there is a capacitor is there, so let us find in the next class. Okay.